Hey everybody, hopefully you are watching this either in class or at home on Friday, what is tomorrow, the 26th, October 26th. This is lesson 22. We started this in class on Wednesday and Thursday. I'm going to summarize what we talked about and then I'm going to continue with it. Your homework, so due on Monday and Tuesday, you have to have completed lessons 21 and lessons 22 homework. You need to come in with questions from the homework if you've got them. On Monday and Tuesday, we're doing lesson 24, so I'm actually skipping lesson 23. We're doing lesson 24 on Monday, which is a review for the test, and then your tests are on Wednesday and Thursday. On Monday and Tuesday, you're also going to have your memory quiz, which I will post a study guide for. Okay, so the relationship between continuity and differentiability is what we're looking at. And there are three reasons that a function would not be differentiable at a specific number, x is equal to c. And I want to just talk about those in general first, and then I'll look at the details. The first is that the function is not continuous, because as we talked about in class, the derivative is the slope of a tangent line, but if a graph doesn't exist somewhere, then you can't have a tangent line where the graph doesn't exist, and so you can't have a derivative. So if the function is not continuous, we talked about that this function is not continuous at -1 and 1, and therefore it is not differentiable at -1 and -1 and +1. All right. In 7th hour, we found the derivative on the calculator, and it just gave us a blank. There was no answer there because there was no y value. But by hand, what I did just now is took the derivative by hand using the quotient rule. So I did low d high minus high d low over low squared. And then if I plug 1 into that, so if I'm plugging 1 into the derivative, when I plug it into the denominator, 1 squared minus 1, I end up with 0 in the denominator. It doesn't even matter what my numerator is, which is why I just left those blank. What matters is that I get a 0 on the denominator. That tells me that f prime of 1 does not exist, and that the function is not differentiable at 1. The second reason that a function may not be differentiable at a point is if the function has a vertical tangent line at a particular x value. So if this is my tangent line, all right, so I have to get vertical here before I can switch from curving up to curving down. This point at x is equal to 0 is a point of inflection where I change from curving up like a cup to down like a frown. And at that point, to change curvature, your tangent line had to turn vertical and then, or become vertical and then switch to curving the other way. So at a vertical tangent line, so if this is my tangent line and it's vertical, I know that this has no slope. All right, so that's the second reason, and we're just basically giving an example here. This example serves a couple of purposes. The first is to remind us how to show that a function is or is not continuous using the three-part definition. So we did that in class. First, the function was defined, then the limit existed, then the value equaled to the limit, and therefore the function was continuous at 0. And then on our calculators lied to us here, so I'm going to be asking my group of teachers about this tomorrow, but by hand this is very clear. If I find f prime of 0, I found the derivative of x to the 1/3 plus 2, which is just 1/3 x to the -2/3. I plug in 0 to that and I get 0 on the denominator. That means that the derivative is not defined at 0, and another way to say that is that the function is not differentiable at 0. Okay, so that's where in 7th hour, because if you put it in your calculator, we got 100, and I don't know why. But anyway, so that's where kind of lost it in 7th hour. The third reason that a function may not be continuous or is not continuous at a particular value is if there's a sharp turn, or sometimes it's called a cusp, a C-U-S-P, of a graph. And this happens when the derivative from the right is not the same as the derivative from the left. So let's see, in second hour today, second hour, seventh hour, who knows, we were talking about this is if look at this as these are my two tangent lines. So my highlighter and my pen are a couple tangent lines. All right. From the right, this is my tangent line coming from the right side of my absolute value function. And from the left, this is it. So from the right and the left, they give me, I've got different slopes, different tangent lines, and so they are not going to be the same slope from the left and the right at x is equal to 0. If I have a smooth curve like a polynomial, and I want to look what is the tangent line at a particular point, if I compare my tangent, or what is the slope at a particular point, so what is the slope of the tangent line there, if I compare my tangent line from the left and my tangent line from the right, those two tangent lines will eventually become the same tangent line. If I get infinitely close, if my tangent line gets infinitely close to this dot, all right, then it will become that tangent line. And if my tangent line from the right gets infinitely close here, these two tangent lines, they become the same tangent line. So the slopes from both sides become the same slope. All right, hopefully that makes some sense, but we're going to do some analytical practice with that also. But on a graph, that just means it's going to look like a sharp point, like in an absolute value, or a cusp, like in this graph here. So this is x to the 2/3 plus 3. All right, again, it's got a sharp point at x is equal to 0. First question says, based on the graph, is the function continuous at x is equal to 0? So I just quickly went through and showed that yes, the function is continuous at x is equal to 0. But then we want to say, is the function differentiable? I found the derivative and I ended up with 0 on the bottom again, which when I plugged in 0, and so the derivative did not exist. All right, so all in all, what we, besides for a review of continuity, what we know right now is a function cannot be differentiable if it is not continuous. But if a function is continuous, it can be differentiable, right? If a function is not continuous, of course it cannot be differentiable. So you must be continuous to be differentiable. But if I told you that a function was differentiable at x is equal to some value c, then because of that, what we've been talking about, you know that that means that the function must be continuous. So if a function is differentiable at x is equal to c, it must be continuous at x is equal to c. All right? If something is continuous, it can be differentiable, but if I tell you something is differentiable, it must be continuous. This is like square is a rectangle, but a rectangle isn't a square kind of argument. And you want to take this little nugget here that we're going to fill in. We know now that differentiability implies continuity. Okay? Differentiability implies continuity. So if I tell you that a function is differentiable at a point, or if I tell you that a function is differentiable everywhere, then that means the function is continuous everywhere. And that is important in a lot of the things that we will do. So in order for a function to be differentiable at an x value, two things must be true. The function must be continuous, please make sure you're writing in these notes as I'm showing them. I went quicker through the first three because we had gotten through a lot of that in class. But your notes need to be filled in as you're watching this. So for a function to be differentiable at a value, the function must be continuous. And then here, this is what we're talking about with the third idea, that the derivative from the right must be the same as the derivative from the left. Or the derivative from the left, which would be the limit as x approaches a from the left of the derivative function, must be equal to the limit as x approaches a from the right of the derivative function. Okay, so that's just saying if I'm looking at some value x is equal to a, then the values of the slope must be the same from the left and the right. Those tangent lines have to be becoming the same tangent line. Okay, so at this moment I'd like you to sketch two graphs of two functions that are not differentiable at x is equal to -2 for two different reasons. So just pause the video and draw those. So you can use one of three reasons, which could be that a function is discontinuous at a particular value. So let's say, all right, discontinuous. So that could be a hole or it could be an asymptote. If my function is not continuous at x is equal to -2, then at x is equal to -2, I have no tangent line there, right? I can't find the slope at this point because the point doesn't exist. All right, so that's one reason. And then let's see, I could have a sharp point. So at -2, let's do this guy. Okay, so a sharp point. All right, so your graphs need to show, one of them could have some kind of sharp point. It doesn't have to be the same as this, but a sharp point or turn of some kind. And then discontinuity could be an asymptote, could be a hole, just where the function is not continuous. Okay, I'm on page 113 now. It says, for what x values is the function below continuous but not differentiable? So continuous means that I'll be able to draw without picking up my pencil through that x value, but not differentiable. So if it's continuous but not differentiable, that means that this is going to be at a sharp point. So as I'm going through this graph, I'm continuous until here, but I have a sharp point at -3. So my function is not differentiable at -3, but was continuous because I could draw through. Now I'm discontinuous at -2, so I'm also not differentiable there, but this question wants to know where I am continuous. So I can skip over -2. Let's see, smooth curves, so that's fine. All right, I've got a discontinuity at x is equal to 0. That's a vertical asymptote. So I'm discontinuous there, and I'm looking for where am I continuous, so I'm just going to keep going. Smooth curves. Smooth curves means I'm continuous because I don't have to pick up my pencil, and also I'm differentiable at smooth curves. But then right here it stops being a smooth curve and it's a sharp point. I don't have to pick up my pencil to draw through there. I am continuous at x is equal to 2, but because it's a sharp point, I'm also not differentiable at x is equal to 2. And then keep going, smooth curves, so no sharp points, no picking up my pencil, smooth curve. I've got this other dot here, which is, I know it's kind of hard to say, but this is supposed to be a vertical tangent line, because notice I'm switching from being concave down to concave up, and watch my tangent line. Vertical and then switches. So here, if I put a tangent line right there, it would be vertical. And so I can draw through that point without picking up my pencil. So I am continuous at 5, but my function is not differentiable at 5. right, so that's what on a graph you need to be able to pick. And then now fun math. Okay, so we've got a graph here, g of x, or a function here. G of x is equal to the square root of x plus 1 from 0 to 3 and 5 minus x from 3 to 5. We want to know first, is the function continuous at x is equal to 3? You're going to show the complete analysis using the three-part definition. I want you to do that. I want you to pause the video and do that. And then you're also going to, then we're going to come and do this. So pause, do your continuity, please. All right, I'm looking to see, is the function defined at 3? So remember, of a piecewise function, I have to plug 3 into the correct piece, and the top piece is the one that includes 3. So that's equal to the square root of 3 plus 1. I know you can do that in your head, but just write it down. You're telling me, you're telling the reader what part you're plugging things into, and it's just better. Okay, so g of 3 is defined. The limit as x approaches 3 from the left is that same top piece of the function. We already found that value, so you don't have to do that again. The limit as x approaches 3 from the right is 5 minus 3, which is 2. Remember that I want you to summarize this for me. What does knowing each of those values tell me? This tells me, so the limit as x approaches 3 of g of x exists. All right, this is my work, but this is the first condition, this is the second condition. My third condition is that g of 3 is equal to the limit as x approaches 3 of g of x. All right, that's my third condition. And that means therefore, so steps 1, 2, and 3, and then therefore, g of x is continuous at x is equal to 3. Okay, is the function g of x differentiable at x is equal to 3? Just because something is continuous, it does not mean it's differentiable, right? Because in this example, we picked 3 places on the graph where the function was continuous, but not differentiable. So what we're going to do here is look at that rule. Let me see, where is that? This part. In order for a function to be differentiable at a value of x, then the function had to be continuous, and we just showed that. And then the limit from the left of the derivative has to equal to the limit from the right of the derivative. So what we're going to do is take the derivative of this piecewise function. And the derivative of a piecewise function is just the derivative of each piece. So remember, let's see, the square root of x plus 1, remember, is x plus 1 to the 1/2. So the derivative of the square root of x plus 1 piece is 1/2 x plus 1 to the negative 1/2 times 1, because this is a chain rule. I don't have to write the times 1. And then that is from 0 to 3. And these change to open intervals now. All right, they were closed on the function, but you can only be differentiable on an open interval. And so this now changes to open at 0 and at 3. All right, and then the derivative of 5 minus x is negative 1 from 3 to 5. Okay, so this is our derivative, and now we're going to see if the limit from the left of the derivative is equal to the limit from the right of the derivative. The limit as x approaches, and we're still looking at 3 from the left of g prime of x. All right, so the left is going to be the top piece, is equal to 1/2 times 3 plus 1 to the negative 1/2. 3 plus 1 is 4, This is the square root of 4 in the denominator. So this ends up being 1/2, this 1/2, times the square root of that in the denominator, so 1/2, so this is 1/4. So the limit as x approaches 3 from the left of the derivative is 1/4. And then the limit as x approaches 3 from the right, well, that's just a constant, so it's still going to equal that constant. Does the left limit equal to the right limit? No. All right? 1/4 is not equal to -1. The limit from the left of the derivative does not equal the limit from the right. Therefore, and so this is my sentence that I'm filling in. Therefore, g of x, and this was just circle one, do you think it is or is not differentiable at x equal to 3? Because the limit from the left and the limit from the right of the derivative did not equal, this function is not differentiable at x is equal to 3 because the left limit of the derivative does not equal to the right limit. So this is very similar to my continuity statement. This is a differentiability statement, and now I'm looking at my derivative functions. Okay. 114 on the back, example 3. Let f be defined by this piecewise function. For what values of k and p will f be continuous and differentiable at x is equal to 1? All right, you have answered questions like this before where you were looking where a function was continuous, and so you set up the limit from the left and the right. We're going to do that same stuff. We're looking for where it's continuous and where the function is differentiable. So we're going to set up two limit equations. And the first is the limit equation we get if the function is continuous at x is equal to 1. If a function is continuous at x is equal to 1, we know, again this is unit 1 step, but we know that the limit as x approaches 1 from the left of the function must be equal to the limit as x approaches 1 from the right of the function. Now we know that if a function is differentiable at x equal to 1, then the limit as x approaches 1 from the left of the derivative will equal to the limit as x approaches 1 from the right of the derivative. We're going to use this system, this piecewise functions and create these two equations, which will give us two equations, and therefore we will be able to solve for our two unknowns. It says create a system of equations in standard form from your two limit equations and solve for k and p. All right, I actually don't think we're going to use standard form in this case, but I'll show you why. So now let's just bring this limit equation down. The limit from the left of f of x. That means that from the left you plug in 1 wherever there's an x, so you get 2 times 1 minus 1 squared. 2 times 1 minus 1 squared equals the limit from the right, plug in 1 for all of the x values here. 1 squared plus k times 1 plus p. And then let's clean that up. So 2 minus 1 is 1 is equal to 1 plus k plus p. And subtract 1, 0 is equal to k plus p. And that's in standard form. Standard form just means your variables on one side and your constants on the other side. All right, and then do the same thing with the derivative equation. Now you don't have the derivative yet, but I need to find it. So over here I'm going to find the derivative of this piecewise. Okay. And that is going to be the derivative of the top 2x becomes 2 minus 2x when x is less than 1. And the derivative of the bottom piece is 2x plus k is just a coefficient of x. It's a number coefficient of x, and so the derivative of kx is just k. And the derivative of p is just another number. So it's a constant, and so the derivative of that is 0. And so that's gone. This is the derivative of the piecewise function when x is greater than 1. All right, so now when I find the limit from the left of 1, I plug in 1 into the x values up top, so 2 minus 2 times 1 equals to the limit from the right of 1, so that'd be 2 times 1 plus k. And then clean that up, this becomes 2 minus 2, which is 0, is equal to 2 times 1, 2 plus k. Okay, and so now we are ready to solve for k and p. Sometimes this would be another equation in k and p, and we'd have to use elimination. And hopefully you know what I mean when I say that. When you line up your k's and you line up your p's and you line up your constants and you solve by elimination. In this case, I don't have to do that because already here, since p is gone, I can just subtract 2. I know that k is equal to negative 2. And now I can just bring that over here, plug negative 2 in for k, and solve for p. So add 2 to both sides, and p is equal to positive 2. So these two are my answers to the question where it said for what values of k and p will the function be continuous and differentiable. And that happens when p is 2 and k is negative 2. Okay, I want you to try 1 and 2 on your own, and I will put the key for that on the website. I'm not going to walk you through it step by step. I want you to try it, but I will work them out and put them up for you. Okay, muchachos, message me if you've got any questions. I'll be in training, but I will, I'm still sitting there working there for you, so I'd be happy to answer any questions that you've got over the weekend. Bye-bye.